let's get the show on the road here.
Yeah.
All right. We're going to continue on in section 14.1. Did you guys remember what we did last time?
No.
We talked about how to find two things in rational functions. Good. So far in this chapter, we've talked about what a rational function is. We've talked about how to find a vertical asymptote and how to find a rule of discontinuity. How do we find these things?
Asymptotes were not my strong suit.
What's it called? You simplify.
Okay.
Then you, once you really break it all down, you cancel out and put the denominator equal to 0.
Okay, so we simplify the expression and then set denominator equal to 0. And I'm going to write and solve there. That's probably implied. And then any real solutions there become your vertical asymptotes. Okay, how about for the removal discontinuities? We start the same way. And what do we do here? It's not the same thing, but it's close. It's because we're not setting the denominator equal to 0, not the numerator. So we said any factors completely canceled from the denominator equal to 0, and then we solve. Any real solutions to those are our removable discontinuities. So let's look at a quickie example here that'll have both removable discontinuity and a vertical asymptote in it, so we can just kind of square ourselves on the difference between these two things. Okay, so let's say we have y equals x squared minus 5x plus 6 and x squared minus 4. We want to find the vertical asymptotes and or removable discontinuities for this. We start by simplifying. To simplify this, what's the first thing that needs to happen? Factor. Good. How does x squared minus 5x plus 6 factor? Okay, we need two things that add to give us negative 5 and multiply to give positive 6. Good, negative 2 and negative 3. And then how about x squared minus 4? Okay. So what can cancel? The x minus 2's. So to find my vertical asymptote, I'm going to take the simplified piece, the denominator, equal to 0. So there's my vertical asymptote. For the removal discontinuity, I'm going to take the part that's completely reduced from the denominator, set that equal to 0, and solve.
So for
Mhm.
this one cancel out.
It has to be completely canceled, like there can be no x minus 2's left at all in the denominator. But that's all. So it's kind of the same thing, right?
Yeah.
To think they're kind of this, you do it the same way is not far off, right? Little bit of detail there, but not much. Everybody's so far so good? Does this start kind of jogging our memories?
Yeah.
Why don't we do X first? Why do we do that?
Well, so these are types of discontinuities, right? Discontinuities occur when a function is undefined. This function is essentially a fraction, right? When are fractions undefined? When you have a denominator of 0, when you're dividing by 0. If you have a 0 in the numerator for a fraction, what does that make it?
Still,
It's just 0, right? 0 divided by 2 is just 0. So that's fine. That's actually going to turn out to be something else. Significant that we're going to be interested in, but that's why we're not worried about it here.
Okay.
Does that feel okay?
Yeah.
Okay. So moving forward here, let's talk about finding x-intercepts or zeros for a rational function. Now, when is a fraction equal to 0? When its numerator is 0. So that's going to be the same idea here. We're going to simplify the expression. We're going to take this reduced numerator, set that equal to 0, and solve. Any real solutions are our x-intercepts. What's the nice part about all this stuff that we're doing? Well, we've kind of done all these sub-skills before, absolutely. And 2, it all kind of works together, right? The first steps are all the same. It's like simplify and reduce. You only need to do that once, and then you can pick out like all these different attributes out of our function once we've had it simplified and reduced. All right. Okay, let's say, oops. We're going to be finding x-intercepts here. So what's the first thing I need to do? To simplify this, what do I have to do first? Factor. So how does that numerator factor? X plus 6 times x plus 1. Multiplying to give me positive 6, and adding to give me 7.
Oh.
So 6 times 1 is 6, 6 plus 1 is 7. Okay, how about the denominator?
X minus 2 x.
Great. Can anything reduce?
No.
No. So what are we going to do? We just take the numerator. Set it equal to 0. And to solve that, I can then just take each factor and set it equal to 0. So my 2x-intercepts are at -6 and -1. Let's do another. Okay. Who can factor the numerator for me? Very good. This is a skill that you really want to be able to do and do quickly. How about the denominator? Who can do that?
X plus 5 x.
Good. We notice then that the x plus 5s can reduce. So to find the x-intercepts, all I care about is the reduced numerator. I just set that equal to 0 and solve, and I'm done. Everybody okay there? Okay. Next attribute we're going to look at is going to be the y-intercept then. Oh, worth pointing out, I guess, hold on, before we start this, worth pointing out, are we always going to have x-intercepts? No, right? What could happen?
The denominator 0.
What's up, Caden? Okay, so there's two situations where you could end up with no x-intercepts. So let's say we have something like this. X squared plus 1, not factorable, right? X plus 5 are not factorable, it's already prime. So you just take the numerator, set it equal to 0, but I get plus or minus I when I do that, right? That has no real solution to it, so there's no x-intercept. Or, simpler even yet, what if I have no variable in the numerator? Like what if I just have 1 over x plus 5? Right? You set 0 equal to 1. This just, again, has no solution to it, so no x-intercepts. So situations like that can come up. Does that feel okay? No big deal there. All right. Y-intercepts. So So all we need to do for find a y-intercept is just to plug x equals 0 into our reduced function. So let's say we have y equals x plus 3 over x minus 5. Is that is that reduced?
Yeah.
Yeah.
Yeah, right. We can't factor it anymore, so that's reduced. So we just put 0 in. So that's 0 plus 3 over 0 minus 5 just becomes negative 3/5. Or really, we'd probably write it as the point 0 comma negative 3/5, but that's fine.
Should we write our x-intercepts as points as well?
You could. Yeah, you could. Sure. What's the sneakiest thing Mr. Kulik could do? Okay, what if we have something like this?
That was actually undefined.
So you could start by factoring it. We can just take an x out, right? Nothing to reduce, though. So when we plug 0 in, what does that mean? Because what's really happening here? If I look at this, I have a vertical asymptote at x equals 0 and x equals 7. What is x equals 0? That's the y-axis, isn't it?
Yeah.
How are you going to have a place where the y intersects the y-axis if that's where your asymptote is? Oh, yeah. Okay, so Mr. Kulik could do something sneaky there. What else could I do that's sneaky? What if I changed it to 6x over x squared minus 7x? Well, not so fast, homie. Because we can reduce that. So what do you think so what's the y-intercept here? So you guys say that's this, right? What's the problem, though? That's not right. What happened when we did this? So we have a removal discontinuity at x equals 0. That means we can't plug 0 in later on. Boom. So that's like the sneakiest move that Mr. Kulik can pull.
So what is it?
So there is no y-intercept because at x equals 0, we have our removal discontinuity. So there's actually a hole in the graph at 0, -6/7. That's not a point. That's where the location of the removal discontinuity is. That's where the hole in the graph is. So there's like a little tiny point missing. There's 1 point missing from our graph at that location.
So how are you supposed to know that?
Because the removal discontinuity is at x equals 0. It's a removal discontinuity. That's what a removal discontinuity is. It's a hole. It's like 1 point that's missing. And that point that's missing is on the y-axis, which means that I can't have a y-intercept because the place where it would be is missing. It's gone. That's what's going on there. Does that feel okay? Yeah. This is prime note card stuff, like the little procedures on how to find all these things, because it's kind of a hassle, right? A lot of this stuff is, the procedure is very similar, so it's easy to get turned around on. All right. We have one more attribute that we're going to be interested in. All right. So this is, I think, the trickiest thing here in this, talking about the attributes for the graphs of rational functions, is being able to pick out what the horizontal asymptote or end behavior and slant or slant asymptote / end behavior is. So let's say we have some rational function that's of the form P of x over Q of x. So reminder, the P of x is our numerator, the Q of x is our denominator. So there's 3 cases. The first case is if the degree of P of x is less than the degree of Q of x. When I say degree, what do I mean? The highest exponent in the polynomial, exactly right. If that's the case, we're going to have a horizontal asymptote or end behavior at y equals 0. Always y equals 0. So if the degrees are equal, then we'll have a horizontal asymptote or end behavior at the leading coefficient of the numerator divided by the leading coefficient of the denominator. Case 3 is the bad one.
Three of them are. Or-
What's up, sir?
Get out. How long till you're...
We have lunch at 12:20.
Okay. I'll be back to...
Okay.
That was
All right. So case 3, when the degree of the numerator is greater than the degree of the denominator, we're going to have some kind of slant asymptote or end behavior, where the equation is going to be y equals the quotient from the division problem p of x divided by q of x. That's the worst case because you have to do the polynomial division or synthetic division depending on the situation. And that can be time consuming, right? Yeah. The good news is that we just did a bunch of it, so we should be still in a little bit of practice, as opposed to this was like did not directly follow chapter 13. It was like 5 chapters later. It'd be like, oh, remember that? No, not really. Hopefully now we still kind of.
You can pick between either or. I think you just like you have to follow a certain one.
A certain one what?
Like the division.
Depends on the problem.
Oh.
Polynomial division will always work. Synthetic division sometimes works. I know you do. Well, it's the shortcut. Why would you like the long one? The benefit of the long one is it always works. The disadvantage of the shortcut is it doesn't always work. All right. Okay, so let's say that we have x minus 7 over x squared plus 6x minus 16. Which case are we in? Good. This is case 1 because the degree of the numerator is 1. The degree of the denominator is 2. So what does that tell me is going on in case 1? Y equals 0. Now technically, this is actually an end behavior, not an asymptote. What's the difference? So if I have something like this, that's like an asymptote, right? It's approaching that line but not crossing it. This is not an asymptote. It's technically an end behavior. What's the difference? It crossed, right? Now, how can Mr. Kulik tell by looking at this thing that we have that it's going to cross and not just be an asymptote? What's y equals 0? It's the x-axis, isn't it? Is that going to have an x-intercept? That's how I know that it's an end behavior, not an asymptote, just on sight. Is I can look at it and go, oh, that has an x-intercept. It's got to cross the x-axis. Now, is Mr. Kulik on the test going to care whether you call something an end behavior an asymptote?
No.
No. Well, we're in class. We're going to be correct about things. I'm going to try to use the correct vocabulary. But that's not a standard I would apply to you. Fair? Sure. You're welcome.
Oh, this is case 2.
Good. How did you know?
Degrees are equal.
So it's a degree 2 on top and a degree 2 on bottom. So this is case 2. So it's the leading coefficient of the numerator, which is
2.
and over the leading coefficient of the denominator, which is 3. Can Mr. Kulik tell on site whether it's going to be end behavior and asymptote? No, he cannot. Nor could you. It'd be a pure guess. It's just a 50-50. But that's not bad odds if you're going, if you're a baseball player and you're 50-50 on everything, you're Hall of Famer. You're the greatest player that's ever lived. If you're a basketball player and you're 50-50 on everything, you're pretty darn good too. Well, not if you're like 7 feet tall and you stand next to the basket. There you should be well over 50-50.
Yeah.
But
On March, whatever, of 2023.
Shannon, you made my.
okay,
Stop it.
which situation are we here?
We are in 3. Gotta be 3 because of degrees.
Yep.
I guess it was 3 because you already did 1.
Well, that's not guess. That's 200%.
Okay. So this is case 3 because we have a degree 2 divided by a degree 1. So here we have to do some division. Let's look at our division problem. Can we do synthetic division in this
Yes,
case?
we can because it's monic.
Yeah, so the denominator,
It's monic.
monic is the term. So if our denominator is degree 1 with leading coefficient 1, that's our best case scenario because now we can polynomial or we can do synthetic division rather than polynomial division. Everybody's okay with the setup?
So when it's not monic, then we have to do the long division.
Yes. And what do these numbers at the bottom mean?
What's your answer?
What's the 15?
It's our remainder.
Mm-hmm. Constant and x coefficient, right? The only part we care about is the quotient. That's everything but the remainder. So our slant asymptote is y equals x minus 6. It does not matter to us in determining the slant asymptote at all. And we're going to pause here because, well, it's like we have lunch in like 3 minutes and I don't want to get into something new. This feels like a good stopping point. So we're just going to pause here.
Yeah.
Plan for the rest of the class. You guys can work on 1 through 8. And then 13 through 16, you can find the attributes, but you don't need, we haven't talked about how to get a graph out of that stuff yet, so don't worry about that. If you manage to finish that and or would prefer to work on delta maths, you guys should now be able to go and do I think all of the sections from the Delta Math now. I
So
think,
do for Sunday.
yeah, if you worked on it Sunday and you're like, yeah, we eventually got to stuff I didn't know how to do, and you stopped, you should now be able to finish that if you want to finish that. Either is fine with me, but we should be working on something math-related being productive. So whether it's finishing your Delta Math,
All sections.
or you should be able to do 1 through 8, 13 through 16, but don't graph those ones, even though the directions ask you to. We haven't covered that much yet. Just do the find the attributes part. And next class, we'll talk about how to put all this stuff together and get a graph out of it, and limit notation and stuff like that.
A little bit of noise.